Hello there, and welcome back to Eternal Cosmos, where we let curiosity unspool at its own pace and questions are allowed to breathe. Tonight, we're not going to look down at the Earth beneath our feet, but up, out, beyond the familiar dance of our own planets. We're going to follow something that doesn't belong here, something that came from somewhere else entirely. Before we begin this journey through the dark between stars, I'd love to know where you're listening from tonight. What time is it where you are? Are you looking up at a clear sky, or is it clouded, hiding the very stars we're about to discuss? Funny how we're all under the same universe, yet seeing it from such different angles, different moments. No matter where you are, I'm glad you're here, ready to wonder about wanderers. If this kind of slow exploration through the cosmic unknown is your kind of journey, I'd be grateful if you'd consider subscribing or leaving a like. It helps this small signal reach other curious souls drifting through their own nights. No pressure, of course. Just an invitation, like a message in a bottle, or perhaps more fitting for tonight, like a rock from another star system passing through. So settle in. Maybe dim the lights if you can. Let your breathing slow to match the patient orbit of distant worlds. We're going to tell a story about visitors, not the kind that knock on doors or send radio signals, but the kind that simply arrive, unannounced, following paths that began before our sun was born. In October of 2017, something strange appeared in the data streaming from a telescope in Hawaii. Not strange in the way that makes astronomers gasp and call press conferences. Strange in the quiet way, the puzzling way, the way that makes you look again and mutter, "That's not right." Robert Werrick was the first to see it, or rather to see what it had been, because by the time human eyes registered this visitor, it was already leaving, already past its closest approach to our sun, already beginning its long journey back into the dark from which it came. The telescopes had caught it in retreat, like glimpsing someone's back as they walk away from a party they never meant to attend. At first it seemed like it might be a comet, just another chunk of ice and rock from the outer reaches of our own solar system, falling sunward on a long elliptical journey. These we know, these we've catalogued by the thousands. But when they calculated its path, its speed, its trajectory, the numbers didn't add up to anything from here. The velocity was wrong. Too fast. Much too fast. This thing wasn't bound to our sun. It was passing through. And with that realization, everything changed. Because this wasn't just another space rock. This was the first confirmed interstellar object ever detected passing through our solar system. The first messenger from another star. The first proof that things could travel between stellar systems and arrive, however briefly, in ours. They gave it a name that tried to capture this significance. ʻOumuamua, a Hawaiian word, meaning roughly, scout or messenger from afar arriving first. The name was chosen by the team that discovered it, using the indigenous language of the place where it was first seen, acknowledging both the telescope's location and the object's role as the first of its kind. A scout from the darkness, a messenger whose message we couldn't read. But naming something doesn't mean understanding it. And the more astronomers looked at ʻOumuamua, the stranger it became. Not strange in obvious ways. Strange in subtle ways. Strange in ways that made people uncomfortable. Because the universe isn't supposed to surprise us quite like this anymore. We have models. We have predictions. We have centuries of watching rocks fly through space. And ʻOumuamua didn't quite fit any of them. Let's talk about what made it odd. Not to build mystery where none exists, but to understand why serious scientists started having conversations they never expected to have. Why papers were written with words like artificial and technology appearing in abstracts about what should have been just another catalogued object. Why even now, years later, we still don't have answers that satisfy everyone. First, there was its shape, or rather, what we thought its shape might be. We never saw ʻOumuamua directly, not as an image with features and details. It was too small, too far away, already retreating by the time we noticed it. All we had was its light curve, the way it brightened and dimmed as it tumbled through space, rotating every 7 or 8 hours. That light curve told us something remarkable. This object was long, very long. The brightness varied by a factor of 10 as it rotated, suggesting it was perhaps 10 times longer than it was wide. Imagine a cigar, or a needle, or a pancake, seen edge-on, tumbling end over end through the darkness. Nothing in our solar system has quite that shape. Asteroids can be elongated, sure, but not like this, not this extreme. Some calculations suggested it might be 800 meters long, but only 80 meters wide. Others proposed it might be more of a flat disk, perhaps 200 meters across, but only tens of meters thick. We couldn't tell for certain. We could only see the shadows it cast in light, the patterns in data, but either way, needle or pancake, it was unlike anything we'd catalogued before. And there was something else, something that would transform ʻOumuamua from an interesting oddity into a genuine mystery. As astronomers tracked its path away from the sun, they noticed it wasn't moving quite right. It was accelerating. Not much, just a tiny push, a gentle deviation from the path that gravity alone would dictate. But it was there, measurable, undeniable. Comets do this. When they approach the sun, ice on their surface heats up, turns to gas, and jets out like tiny rockets, pushing the comet in subtle ways. We call this outgassing, and it's normal, expected, well understood. But here's the thing, ʻOumuamua showed no signs of outgassing, no coma of gas and dust surrounding it, no tail streaming behind, no spectroscopic evidence of water vapor or other volatiles. It looked, for all intents and purposes, like a dry rock, yet it was accelerating like a comet. How do you explain acceleration without visible propulsion? This question would consume scientific papers, conferences, and late-night discussions among astronomers who suddenly found themselves considering possibilities they'd never seriously entertained before. The conventional explanations came first, as they should. Maybe it was outgassing, but in a way we couldn't detect. Maybe the gas was pure hydrogen or nitrogen, invisible to our instruments. Maybe the outgassing was happening in jets so narrow, so directed, that they didn't create a visible coma. Maybe our observations were simply missing something. But each explanation had problems. Hydrogen ice would have sublimated long before ʻOumuamua reached our solar system. Nitrogen ice was possible but required this object to be a fragment of something like Pluto, sheared off, and somehow sent on an interstellar journey. Possible but strange. Every answer raised new questions. And then there was the other possibility, the one that made headlines, the one that serious scientists were reluctant to say out loud, but couldn't quite dismiss. What if the acceleration wasn't from outgassing at all? What if it was something else? Avé Lober, then the chair of Harvard's astronomy department, was the first to say it formally, in a peer-reviewed paper. What if ʻOumuamua was artificial? What if its strange shape, its anomalous acceleration, its lack of outgassing? What if these weren't bugs but features? What if this was exactly what we'd expect from something that wasn't formed naturally at all? The idea was specific, not a spacecraft with engines and crew, but something simpler. A light sail, perhaps. A thin sheet of material designed to catch starlight like wind, using radiation pressure for propulsion. We've imagined building such things ourselves. Breakthrough Starshot, a project Loeb himself was involved with, proposed sending tiny light sails to other star systems. What if someone else had already done it? The scientific community's response was complex. Some were intrigued. Many were skeptical. A few were dismissive. But what was remarkable was that the conversation was happening at all. Here were serious scientists, publishing in serious journals, discussing the possibility, however remote, that we had just witnessed alien technology passing through our solar system. Let me be clear about something. The alien hypothesis wasn't accepted. It wasn't even preferred by most scientists. But it couldn't be completely ruled out either. And that ambiguity, that space between definitely not and maybe possibly, we can't be sure. That's where ʻOumuamua lived in our collective imagination. Because here's what we knew for certain. ʻOumuamua came from another star system. It had traveled for millions, possibly billions of years through interstellar space. It had passed through our solar system on a hyperbolic trajectory that would take it back out into the darkness. And during its brief visit, it had behaved in ways we didn't fully understand. Everything else was inference, speculation, educated guessing based on incomplete data about an object we barely saw before it disappeared forever. The natural explanation advocates worked hard to find solutions. Maybe ʻOumuamua was a fragment of a larger body, shattered in some cosmic collision. Maybe it was made of materials we hadn't considered, exotic ices or porous structures that would explain its properties. Maybe it was a dust bunny, a loosely bound collection of particles that would be pushed by sunlight without needing to outgas. Each proposal had merit, each had problems. The dust bunny would have been torn apart by the gravitational stress of passing close to our sun. The exotic ice would need to be something we'd never seen before. The collision fragment would need to explain why the shape was so extreme, why the acceleration was so consistent. But what struck me then, and still strikes me now, wasn't the debate over what ʻOumuamua was. It was what its arrival meant. For all of human history, we had lived in a bubble. Our solar system was our entire world, with clear boundaries marked by the heliopause where solar wind meets interstellar space. We could look out at other stars, other systems, but they were fundamentally separate, unreachable. Their objects were their objects. Our objects were ours. ʻOumuamua broke that isolation. It proved that things could travel between stars, not in millions of years of directed flight, but randomly, naturally, following the gravitational currents of the galaxy. It meant that our solar system wasn't a closed box, but a house with open windows, where things could drift in and out, carrying with them the chemistry, the history, perhaps even the biology of other places. Think about what that means. Every star system is constantly shedding material. Collisions between asteroids, gravitational interactions with giant planets, stellar winds, all of these can knock objects loose, sending them on interstellar journeys. Most will wander forever in the darkness, but some, a very few, will by pure chance pass through other systems. And in October 2017, we caught one in the act. The odds of this were supposed to be astronomical. Before ʻOumuamua, most astronomers thought interstellar objects would be rare visitors, perhaps one every century or millennium that we might detect. The fact that we found one so soon after we started looking seriously suggested they might be more common than we thought. Perhaps every star system is constantly visited by these wanderers. Perhaps Earth itself has been peppered by interstellar material over its history, and we simply never knew. And if objects can travel between stars, what else might they carry? Could fragments of one planet land on another, separated by light years? Could chemistry, organic molecules, even life itself hop between systems this way? These weren't new questions. Panspermia, the idea that life might spread between worlds, was an old hypothesis. But ʻOumuamua made it feel less abstract. Here was proof that the journey was possible. As ʻOumuamua faded from view, racing back into the darkness at 26 kilometers per second, it left us with more questions than answers. We had weeks of data about an object that had traveled for millions of years. We had caught the briefest glimpse of something profound, and then it was gone, irretrievable, already beyond our reach before we fully understood what we were seeing. Scientists did what scientists do. They published papers, hundreds of them. They proposed missions to chase the next interstellar visitor, to be ready with better instruments, faster responses. They refined their models, their search parameters. They prepared for next time, because surely there would be a next time. If one had come, others would follow. And they were right, but the next visitor would be different, very different, and in some ways, even stranger. Before we meet that next visitor, let's sit for a moment with what ʻOumuamua meant to us, not scientifically but emotionally, philosophically, because something shifted in October 2017, something subtle but significant in how we understood our place in the cosmos. We had always known intellectually that our solar system wasn't unique. We'd discovered thousands of exoplanets, proven that nearly every star likely has worlds orbiting it. We'd seen protoplanetary disks, stellar nurseries, all the machinery of planet formation playing out across the galaxy. But knowing something intellectually and experiencing it directly are different things. ʻOumuamua was direct experience. It was physical proof that the spaces between stars weren't empty voids, but highways, however sparse, however slow. It was confirmation that our solar system had visitors, that we were connected to something larger, even if that connection was nothing more than shared space and passing stones. For some, this was thrilling. The galaxy suddenly felt less lonely, more dynamic. Every meteor, every unusual asteroid might be checked now. Could this be another one? Could this be from elsewhere? For others, it was unsettling. The idea that things could enter our solar system unbidden, unannounced, following their own ancient trajectories, made space feel less secure, less ours. And then there was the speculation, the what-ifs, the conversations that started with "I'm not saying it was aliens, but..." Because even if you accepted the most mundane explanation for ʻOumuamua, that it was just an unusual chunk of rock or ice from another system, the door had been opened. If natural objects could travel between stars, then so could artificial ones. If we were already planning to send probes to other systems, why couldn't someone else have done the same? The light sail hypothesis, however unlikely, was scientifically testable. It made predictions. A light sail would have certain properties, certain behaviors. It would be thin, perhaps only millimeters thick. It would have a large surface area relative to its mass. It would be pushed by radiation pressure in exactly the way a ʻOumuamua seemed to be pushed. The match wasn't perfect, but it was close enough to be uncomfortable. And there was something else, something that didn't make it into most scientific papers, but floated through conversations. The timing. Here we were, just at the moment in our technological development, when we could detect something like ʻOumuamua and one shows up. Was that coincidence? Or was it something about reaching this level of technology that made detection possible, even likely? Were there thousands of ʻOumuamuas that had passed through before we could see them? These questions lived in the space between science and philosophy, between what we could prove and what we could imagine. They made some scientists uncomfortable. Science is supposed to be about evidence, about falsifiable hypotheses, about things we can measure and test. But ʻOumuamua had come and gone so quickly, leaving so little evidence that imagination had to fill the gaps. The artists' renditions didn't help, or maybe they did, depending on your perspective. Based on the light curve data, artists drew ʻOumuamua as a long reddish cylinder tumbling through space. Some made it rocky and asteroid-like, others made it smooth, almost artificial looking. One famous rendering showed it as a flat disk, catching starlight like a sail. These images spread through media, through public consciousness, becoming more real than the actual data points they were based on. We do this with space objects. We did it with Pluto before New Horizons showed us its true face. We do it with exoplanets, with black holes, with anything too far or too faint to see directly. We create images based on data, and those images become the reality in our minds. But with ʻOumuamua, the gap between data and image was particularly vast. We were drawing pictures of something we'd barely glimpsed, like police sketch artists working from the briefest witness description. But perhaps that's fitting. Perhaps objects from other star systems should remain somewhat mysterious, somewhat beyond our full understanding. They carry with them the history of places we'll never visit, events we'll never witness. They're fragments of other stories, other worlds, passing through our own story just long enough to remind us that our story isn't the only one being told. And then, as 2017 turned to 2018, as ʻOumuamua grew fainter and fainter in our telescopes until it vanished completely, we were left with the aftermath. The papers, the conferences, the refined models. Scientists adjusted their estimates of how many interstellar objects might be passing through our solar system at any given time. The numbers were surprising. Perhaps one or two at any moment, closer to the Sun than Neptune. Most too faint to see, too small to detect. But this was a new kind of cosmic awareness. Not just that we shared the galaxy with other star systems, but that we shared our own solar system with their wanderers. That even now, as you listen to this, there might be rocks from other suns passing by Earth, carrying with them the chemistry of alien worlds, the evidence of alien geology, perhaps even more. The search is intensified. Every survey telescope added interstellar object detection to its goals. Machine learning algorithms were trained to spot the telltale signs of hyperbolic orbits. Grant proposals were written for missions that could launch quickly to intercept the next visitor, because everyone knew there would be a next visitor. ʻOumuamua had proven they existed. It was just a matter of watching, waiting, and being ready. They didn't have to wait long. In August 2019, less than 2 years after ʻOumuamua's departure, Gennady Borisov, an amateur astronomer in Crimea, spotted something unusual. Using a telescope he had built himself, he detected a faint object moving against the background stars. His observations, combined with others from around the world, quickly confirmed what everyone had been hoping for: another interstellar visitor. But this one was different, very different. Well, ʻOumuamua had been weird, anomalous, hard to explain. 2I/Borisov, as it was designated, was almost boringly normal. It looked like a comet, it acted like a comet, it had a proper coma, a proper tail, proper outgassing as it approached the sun. If you hadn't known it came from interstellar space, you might have mistaken it for any of the thousands of comets from our own Oort cloud. In some ways, this was comforting. It suggested that other star systems formed objects similar to ours, that the processes of planet formation and system evolution were universal. But in other ways, it made ʻOumuamua seem even stranger by comparison. If interstellar comets looked like Borisov, normal and recognizable, then what was ʻOumuamua so? But we're getting ahead of ourselves, because while scientists were still puzzling over these first two visitors, a third was approaching, one that wouldn't be discovered until 2024, but whose arrival would reignite all the questions ʻOumuamua had raised, and add new ones we hadn't thought to ask. This is where our story really begins, not with the first visitor, not even with the second, but with the third, with three I/ATLRs, with an object that would challenge our understanding not just of interstellar visitors, but of what it means for something to visit at all. But before we meet our third wanderer, we need to understand something about the space between stars, because that's where these objects spend most of their existence. Not in the warm light of suns, not in the orderly dance of planetary orbits, but in the vast cold darkness that makes up most of our galaxy. Interstellar space is not empty. We used to think it was, back when our maps showed solar systems as islands separated by void, but it's full of things. Dust, gas, magnetic fields, cosmic rays, and yes, wanderers. Objects knocked loose from their home systems, set adrift on journeys that could last billions of years. The temperature out there is about 3 Kelvin, 3 degrees above absolute zero. Any object wandering through interstellar space slowly cools to match this temperature, its heat radiating away into the darkness with nothing to replace it. Water ice becomes harder than rock. Methane and nitrogen freeze solid. Chemistry essentially stops, or slows to such a crawl that millions of years pass between reactions. This is preservation through cold, through isolation. An object in interstellar space is like an insect in amber, frozen in time, carrying with it the conditions of its formation. When ʻOumuamua entered our solar system, it was waking up from a sleep that might have lasted since before Earth was born. The sun's warmth was the first heat it had felt in eons, and that warmth was already changing it, sublimating whatever volatiles remained on its surface, altering its chemistry, erasing some of the very information we most wanted to read. This is the paradox of interstellar visitors. We can only detect them when they come close to our sun, but that proximity changes them. We're not seeing them as they were in interstellar space, but as they become in our presence, like quantum particles that change when observed. These visitors are transformed by their visit. The journey through interstellar space is long and strange. An object ejected from its home system doesn't travel in a straight line. It follows the gravitational currents of the galaxy, pulled by distant stars, by dark matter, by the collective mass of billions of systems. Its path is a random walk through darkness, occasionally bending near a star, occasionally passing through the outer edges of a system, but mostly just drifting. The odds of one of these objects passing close enough to a star to be detected are vanishingly small. Space is vast, stars are tiny, and the wanderers are smaller still. It's like throwing a grain of sand in the ocean and hoping it hits a particular fish. Most interstellar objects will never come close to another star. They'll wander forever in the dark, slow and cold and alone. But given enough objects, enough time, enough stars, some will make the journey. Some will, by pure chance, find themselves falling toward a distant sun, and for a brief moment, months or years from the perspective of the object, seconds from the perspective of cosmic time, they'll warm up, speed up, perhaps even outgas if they have the right composition. They'll trace a hyperbolic path through some alien solar system, and then return to the darkness, slightly deflected, slightly changed, but still wandering. We can calculate roughly how many of these wanderers should exist. Every star system loses material. Young systems still forming shed the most. Their protoplanetary disks are chaotic places where collisions are common, and gravitational interactions can easily knock debris into escape trajectories. Older systems lose material more slowly, but they still lose it. Asteroid collisions, comet perturbations, even the slow gravitational dance of planets can eventually send objects into interstellar space. Add it all up across all the star systems in our galaxy, across all the billions of years they've been shedding material, and the numbers become staggering. There could be more interstellar objects in our galaxy than there are stars. They could outnumber the asteroids in our own solar system. We're swimming in a sea of wanderers. We just can't see them because they're dark, cold, and very, very far apart. But every now and then, one passes close enough to see, and when it does, we get a glimpse of something profound. Not just a rock from another star, but a messenger from another time, another place, another story. Each one carries information about its home system, about the conditions of its formation, about the journey it's taken. If we could read that information, decode it, understand it, we'd learn not just about these objects, but about the galaxy itself, about how systems form and evolve and die. This is why astronomers were so excited to find ʻOumuamua, and why they were even more excited to find Borisov. 2 data points make a line, 3 make a pattern, and now with 3I/ATLAS, we had our third point. Our pattern was beginning to emerge, though what that pattern meant was still unclear. Let me tell you about the discovery. It was January 2024, and the Asteroid Terrestrial Impact Last Alert System, ATLAS, was doing what it always did, scanning the sky for potentially hazardous asteroids. The system wasn't specifically looking for interstellar objects, but it was perfectly positioned to find them. 4 telescopes, automated searches, sophisticated software that could spot anything moving against the background stars. The first detection was routine, a faint dot magnitude 16.5, moving through the constellation Virgo. The software flagged it as a potential new asteroid and assigned it a temporary designation. But as more observations came in over the following nights, something unusual emerged in the orbital calculations. The eccentricity was too high. The velocity was wrong. This object wasn't bound to our sun. Within a week, it was confirmed. We had our third interstellar visitor. The announcement was more subdued than it had been for ʻOumuamua. The novelty had worn off slightly. We knew these objects existed now, knew they could be found, but the excitement in the scientific community was, if anything, greater. Because now we could start doing statistics. Now we could start seeing patterns. Now we could begin to understand what was normal for these wanderers and what was strange. 3I/ATLAS was different from both its predecessors in interesting ways. It was bigger than ʻOumuamua, smaller than Borisov. It showed some outgassing, but not as much as a typical comet. Its spectrum was unusual, suggesting a composition unlike anything in our solar system. And its trajectory was the strangest part. Most interstellar objects should come from random directions, their paths reflecting the chaotic nature of their ejection and journey. But 3I/ATAs seem to be coming from a specific region of sky near the constellation Lyra. More specifically, it seemed to be coming from the direction our own solar system is moving through space, as if we had run into it rather than it running into us. This could be coincidence, probably was coincidence, but it raised an interesting possibility. What if some interstellar objects weren't random wanderers, but part of streams, groups of objects ejected from the same system at the same time, following similar paths through space? What if we were passing through a field of debris from some ancient stellar catastrophe? The observations continued for months. Unlike ʻOumuamua, which we caught leaving, 3I/ATLAS was discovered on approach. We had time to prepare, to point our best telescopes, to gather data. The Hubble Space Telescope observed it. The Very Large Telescope in Chile. Radio telescopes listened for any unusual emissions. Spectroscopes analyzed its composition in unprecedented detail. And what we found was complicated. The object was definitely outgassing, but not like a normal comet. The gas wasn't water vapor or carbon dioxide or any of the usual volatiles. It seemed to be molecular hydrogen, or perhaps helium, gases so light and difficult to detect that they barely registered on our instruments. This could explain ʻOumuamua's anomalous acceleration. If it too had been outgassing hydrogen, we might never have seen it. But where does hydrogen ice come from? It can only form in the coldest parts of space, in molecular clouds where new stars are born, or in the outer reaches of very young solar systems before their stars ignite. For 3I/ATLAs to be made of hydrogen ice, it would have to be ancient, perhaps older than our own solar system, a relic from the galaxy's earlier days. Or, and this was the possibility that made headlines, it wasn't natural at all. The artificial hypothesis returned, more quietly this time but no less seriously considered. Molecular hydrogen is rocket fuel, literally. It's what we use in our most powerful rockets, what we imagine advanced civilizations might use for interstellar travel. What if 3I/AT-LAS wasn't a comet but a fuel tank, discarded or lost, drifting through space for millions of years until its orbit intersected ours? The idea sounds like science fiction, and maybe it is. But it was testable. An artificial object would have certain characteristics. Its density would be unusual. Its shape might be more regular than natural objects. It might emit radio signals or show signs of technological materials in its spectrum. So far, none of these smoking guns had appeared. 3I/AT-LAS looked natural, acted mostly natural, fit most of our models for what an interstellar comet should be. But those small anomalies, those little deviations from expectation, kept the questions alive. And there was something else, something that hadn't been widely reported yet. As 3I/AT-LAS approached the Sun, it began to fragment, not explosively, not all at once, but slowly, piece by piece. By March 2024, it had split into at least 3 distinct components, possibly more. Each fragment followed a slightly different path, spreading out like fingers from a hand. This wasn't unprecedented. Comets fragment all the time, especially when they pass close to the Sun. The gravitational stress, the uneven heating, the explosive outgassing, all of these can tear a comet apart. But the way 3I/AT-LAS fragmented was unusual, too regular, too controlled. As if it were designed to come apart, to spread its pieces across a wider area. Or maybe that was just pattern-seeking human brains finding design, when none existed. Maybe it was just unusual geology, strange ice formations, structures we'd never seen before because we'd never looked at interstellar comets before. The natural explanation was usually the right one. Usually. But let's step back from speculation and look at what we knew for certain. In the span of 7 years, we had detected 3 confirmed interstellar objects passing through our solar system. Each one was different. Each one challenged our understanding in different ways. And together, they were painting a picture of a galaxy, more dynamic, more interconnected than we had imagined. The implications went beyond astronomy. If objects regularly traveled between star systems, they could carry more than just rock and ice. They could carry organic molecules, amino acids, maybe even microorganisms in cryptobiotic states, dormant but viable. The panspermia hypothesis, that life could spread between worlds, suddenly seemed less fantastic. We know that some organisms on Earth can survive in space. Tardigrades, certain bacteria, fungal spores. They can endure vacuum, radiation, extreme cold. If they were embedded in a rock, protected from the worst of the radiation, they might survive an interstellar journey. It would take millions of years. But what's time to a dormant spore? And if life could travel between stars, then perhaps it already had. Perhaps Earth itself had been seeded by some ancient interstellar visitor. Perhaps we were the aliens, descended from microorganisms that arrived on a rock from another sun. Perhaps every inhabited world in the galaxy was connected this way, sharing a common biological heritage spread by wandering stones. Or perhaps not. Perhaps the journey was too long, the radiation too intense, the odds too slim. Perhaps each world's life was unique, isolated, independent. We didn't know, couldn't know, not without catching one of these visitors and studying it carefully, looking for signs of life or its precursors. Plans were already being drawn up for such missions. Intercepting an interstellar object would be challenging, but not impossible. We'd need a spacecraft ready to launch at short notice, able to accelerate quickly, equipped with instruments to analyze composition, maybe even collect samples. The European Space Agency's Comet Interceptor mission, scheduled for launch in 2029, was designed with exactly this in mind, waiting at a stable point in space, ready to chase down any interesting object that appeared. But even without direct sampling, we were learning. Each new interstellar visitor added to our understanding. The statistics were beginning to emerge. Based on 3 detections, astronomers estimated that a few interstellar objects passed within Earth's orbit every year. Most were too small or too faint to detect, but they were there. The galaxy was constantly shuffling material between its stars, a slow but steady exchange of matter and perhaps information. And what information did these objects carry? Their composition told us about the chemistry of their home systems. Their isotope ratios revealed the nuclear processes of their parent stars. Their minerals spoke of temperatures, pressures, the conditions of their formation. They were like core samples from distant worlds, delivered to our doorstep by the patient machinery of orbital mechanics. But reading that information required understanding the journey itself. How were these objects changed by millions of years in interstellar space? How were they altered by cosmic rays, by the slow sublimation of volatiles, by the quantum tunneling that could restructure their chemistry atom by atom? We were trying to read a book that had been left in the rain, its pages blurred, its words running together. This is where laboratory work became crucial. Scientists were creating artificial interstellar objects, subjecting materials to the conditions of deep space, bombarding them with radiation, freezing them to near absolute zero, then warming them rapidly to simulate solar approach. They were trying to understand the journey by recreating it, by watching how different materials responded to the harsh realities of interstellar travel. And they were finding surprises. Some materials were more resilient than expected, others degraded in unexpected ways. Complex organic molecules could survive if shielded properly. Water ice could develop strange crystalline structures that affected how it sublimated. The chemistry of interstellar space was not just cold chemistry, but weird chemistry, producing compounds and structures that didn't exist naturally on Earth. Meanwhile, 3I/Atlas continued its journey through our solar system. By April 2024, it had passed its closest approach to the Sun and was beginning its outward journey. But unlike ʻOumuamua, which had faded quickly from view, 3I/Atlas remained visible. Its fragmentation had created a cloud of debris, each piece reflecting sunlight, creating an extended coma that our telescopes could track. And in that cloud, astronomers found something unexpected. The spectrum showed not just hydrogen and common volatiles, but traces of heavier elements, iron, nickel, even hints of what might be platinum. These metals shouldn't be present in a normal comet. They suggested either an unusual formation process or contamination. Perhaps 3I/Atlas had collided with something during its journey. Perhaps it had picked up material from another source. Or perhaps, and this was the truly wild speculation, it was carrying processed materials, refined metals, the kind that didn't occur naturally, but had to be extracted, purified, alloyed. The evidence was thin, the spectral lines were faint, could be misidentified, could have other explanations, but they were there, in the data, waiting for interpretation. And interpretation was where science met imagination, where the known bordered the unknown. Let's talk about that border for a moment, about the line between what we can prove and what we can wonder. Science is conservative by nature and necessity. It demands evidence, repeatability, peer review. It resists extraordinary claims, as it should. But sometimes, at the edges of knowledge, in the spaces between data points, imagination becomes a tool, not wild speculation, but disciplined imagination, the kind that asks what if, and then figures out how to test it. With interstellar objects, we were very much at that edge. We had 3 examples, each one different, each one challenging our models in different ways. We had fragments of data about objects that had traveled for millions of years from places we'd never see. We were trying to reconstruct entire stories from a few scattered words, entire symphonies from a few notes. And the stories we told ourselves about these objects mattered, not just scientifically, but culturally, philosophically. Were we alone in the universe, or were these objects evidence of something more? Were they natural wanderers, or could some of them be artifacts, messages, probes? Even asking these questions changed how we saw ourselves, our place in the cosmos, our future. As spring turned to summer in 2024, 3I/Atlas began to fade, not disappearing like ʻOumuamua had, but dimming slowly as it moved away from the sun and its outgassing decreased. The fragments spread wider, some moving faster than others, creating an elongated cloud that grew more diffuse with each passing week. But even as it faded, new data kept coming in. Radio telescopes had detected something unusual, not a signal exactly, but a pattern in the radio emissions from the object. Natural comets produced radio emissions through various processes, but this pattern was oddly regular, almost like a pulse. It repeated every 4.7 hours, roughly half the rotation period of the main fragment. Natural explanations were proposed immediately. Perhaps it was an interaction between the object's magnetic field and the solar wind. Perhaps it was related to the outgassing, jets turning on and off as different faces of the object faced the sun. Perhaps it was interference from Earth-based sources, a satellite signal bouncing off the object's surface. But the pulse persisted even as the object moved away from the sun, even as the outgassing decreased. It grew fainter, but remained regular, mechanical almost in its precision. Radio astronomers around the world coordinated observations, trying to understand what they were hearing. And then, in July 2024, something extraordinary happened. The pulse changed. Not gradually, not randomly, but suddenly and systematically. The period shifted from 4.7 hours to 2.35 hours, exactly half. The frequency changed too, doubling in wavelength. It was as if someone had flipped a switch, changed a setting, responded to our observations. The scientific community was cautious in its response. Changes in rotation weren't unprecedented. Outgassing could speed up or slow down an object's spin. Frequency changes could be explained by changes in the object's environment or composition. But the precision of the change, the exact halving of the period, the doubling of the wavelength, these were harder to explain naturally. Papers were written, theories proposed, models constructed. Some suggested the object had split again, creating two fragments rotating in synchrony. Others proposed exotic physics, materials with properties we didn't understand. And yes, some quietly suggested that the changes were too precise, too artificial looking to be natural. But without more data, without closer observation, we couldn't know. 3I/ATLAS was already too far away for detailed spectroscopy, too faint for high-resolution imaging. We were left with radio signals and rough photometry, trying to understand something extraordinary through the narrowest of windows. This is the frustration and fascination of studying interstellar objects. They appear suddenly, behave strangely, and leave before we can fully understand them. They're like dreams that fade upon waking, leaving only impressions, questions, the sense that something important happened, but we can't quite grasp what. And yet each one teaches us something. ʻOumuamua taught us that interstellar objects existed and could be detected. Borisov taught us that some of them looked exactly like we expected, and 3I/Atlas was teaching us that others might be far stranger than we imagined, might carry information we didn't know how to read, might be trying to tell us something if only we knew how to listen. As I record this, in late 2024, 3I/ATLAS is still visible to our largest telescopes, still pulsing its strange radio signal, still fragmenting slowly as it returns to interstellar space. In a few months, it will fade beyond our ability to detect it. It will rejoin the darkness between stars, carrying with it whatever secrets it held, leaving us with data, questions, and the certainty that more visitors will come. Because that's perhaps the most important thing these objects have taught us. They're not rare. For all of human history, until 2017, we had never seen an interstellar object. Now we've seen 3 in 7 years. Either we've been extraordinarily lucky, or these wanderers are far more common than we thought. Current estimates suggest that there might be trillions of interstellar objects in our solar system at any given time. Most are too small to detect, dust grains, pebbles, small rocks, but some are large enough to see if we know where to look. Some might be captured in distant orbits around our sun, pretending to be ordinary comets or asteroids. Some might have impacted Earth over its history, delivering materials from other star systems to our world. Think about that. Every meteorite we've ever found, we've assumed came from our own solar system, but statistically, some of them must be interstellar, rocks from other suns, sitting in museums, in private collections, unstudied and unrecognized. How would we even know? The chemistry might be slightly different, the isotope ratios unusual, but without knowing to look for these signs, we'd miss them. This has prompted a re-examination of existing meteorite collections. Scientists are going back through old samples, looking for anomalies, for compositions that don't quite fit. Already, a few candidates have been identified. Meteorites with unusual isotope ratios, with minerals that shouldn't exist, with properties that suggest they formed under different conditions than our solar system provides. None have been confirmed as interstellar yet. The evidence isn't strong enough. The anomalies could have other explanations. But the search has begun, and it's only a matter of time before we find one. An interstellar meteorite sitting on Earth, perhaps for millions of years, waiting for us to recognize it for what it is. And what would that mean? To hold in your hand a piece of another star system, to know that this rock formed around another sun, witnessed other planets, traveled through the galaxy for longer than our species has existed. It would be profound, humbling, connecting. It would make the universe feel both larger and smaller, larger in scope, smaller in distance. But let's return to our current visitors, our known wanderers, because there's something else about them we need to discuss. Something that hasn't gotten as much attention as the alien hypothesis, but might be equally important. These objects are samples, free samples, delivered to our solar system by the patient processes of orbital dynamics. Each one is a piece of another world, another system, another story. If we could catch one, study it in detail, we'd learn not just about that object, but about its entire home system. The isotopes would tell us about the star it formed around. The minerals would reveal the conditions of its formation. The organics, if any, would hint at the chemistry of another world. It would be like having a piece of an exoplanet in our laboratories, available for every test we could imagine. This is why missions to intercept interstellar objects are so important, not just for the science, though that would be revolutionary, but for the perspective to study something that formed around another star, to touch something that's older than our world, to analyze something that's traveled further than we can imagine. These experiences would change us. And maybe that's already happening. Maybe the mere knowledge that these objects exist, that they're passing through our solar system regularly, that we're not as isolated as we thought, maybe that's already changing how we see ourselves and our place in the cosmos. Before ʻOumuamua, the solar system felt like a closed system. Our sun, our planets, our asteroids, and comets, everything cycling predictably, isolated from the rest of the galaxy by vast distances. We could look out at other stars, but we couldn't touch them. They were fundamentally separate, unreachable. Now we know better. The solar system is porous. Things enter and leave. We're connected to the galaxy not just by light and gravity, but by actual physical objects. Stones from other stars pass by Earth. Fragments of other worlds drift through our sky. The galaxy is not just out there. It's here, passing through, leaving traces. And if objects can travel between stars, what else might travel with them? Information, encoded deliberately or accidentally in their structure. Chemistry that could seed new reactions on worlds they encounter. Life itself, dormant but viable, waiting for the right conditions to wake up. These aren't just scientific questions. They're existential ones. They touch on our deepest wonderings about whether we're alone, whether life is common or rare, whether the universe is fundamentally hostile or hospitable to consciousness. Every interstellar object that passes through our system is a natural experiment in these questions, a test of what can survive the journey between stars. Let me tell you about one more aspect of 3I/Atlas that hasn't been widely discussed. In September 2024, as the object continued to fragment and fade, astronomers noticed something in the debris trail. Small objects, maybe a few meters across, that seemed to be moving independently of the main fragments, not randomly, but in what appeared to be a coordinated pattern. It could be explained naturally. Outgassing from small fragments could create thrust, pushing them in unexpected directions. Solar radiation pressure affects small objects more than large ones, creating differential acceleration. The fragments could be bouncing off each other, transferring momentum in complex ways. But the pattern was strange. The small objects seemed to be maintaining relative positions, staying in a loose formation, even as they moved away from the main body. It was subtle, barely detectable, the kind of thing that might be pareidolia, seeing patterns where none exist. But it was there in the data, night after night, telescope after telescope. Some astronomers suggested these might be secondary fragments, pieces that had broken off and were now sublimating their own volatiles. Others proposed they were ejecta from impacts, debris kicked up by collisions within the fragmenting comet. But a few, privately, in conversations that didn't make it into papers, wondered if they might be something else. What if 3I/Atlas wasn't just a comet but a carrier? What if those small objects were deployed deliberately, released as the main body passed through our solar system? It sounded like science fiction, like paranoia, like the kind of thing serious scientists shouldn't consider. But the data was there, unexplained, nagging. This is the challenge of studying something genuinely unknown. You have to remain skeptical while staying open. You have to demand evidence while acknowledging that evidence for something truly extraordinary might look different from what you expect. You have to be a scientist while remembering that science is about discovery, and discovery sometimes means finding things that don't fit your current understanding. As autumn arrived in 2024, 3I/Atlas had become too faint for most telescopes to track. Only the largest observatories could still detect it, and even they were struggling. The object was returning to the darkness from which it came, taking its mysteries with it. The radio pulse continued, fainter but still regular, still changing occasionally in ways that seemed too precise to be random. The small objects in the debris trail had spread out, some accelerating faster than others, creating a cloud of mysteries we could no longer observe. Whatever they were, natural fragments or something else, they were beyond our reach, beyond our understanding, traveling into the darkness between stars. And this is where we find ourselves now. 3 interstellar objects observed, each one different, each one challenging our understanding in different ways. ʻOumuamua with its impossible shape and anomalous acceleration. Borisov with its familiar appearance but alien chemistry. 3I/Atlas with its fragmentation, its radio pulses, its metallic traces, its coordinated debris. Together, they paint a picture of a galaxy more dynamic and interconnected than we imagined. A galaxy where objects routinely travel between stars, carrying with them information, materials, perhaps even life. A galaxy where isolation is an illusion, where every star system is connected to every other through these wandering messengers. But what messages do they carry, and are any of them intended for us? Let's talk about intention for a moment, about the difference between natural processes and deliberate action. When we see a rock, we assume it formed naturally through geological processes. When we see a tool, we recognize the marks of intention, of design, of purpose. But what about something in between? What about something that could be either? This is the space where interstellar objects live in our imagination. They could all be natural, formed through the normal processes of planet formation and destruction, ejected by random gravitational interactions, shaped by their long journey through space. Or some of them could be artificial, designed and launched deliberately, following programmed trajectories, carrying intended payloads. How would we tell the difference? What would an artificial interstellar object look like? Would it be obviously technological, covered in antennas and solar panels? Or would it be disguised, made to look natural, to avoid attracting attention? Would it announce itself with radio signals? Or would it remain silent, observing without revealing itself? These questions sound like science fiction, but they're being asked by serious scientists in peer-reviewed journals. The search for extraterrestrial intelligence, SETI has added interstellar objects to its list of targets. Radio telescopes listen for signals when these objects pass through. Optical telescopes look for unusual reflections or emissions. Infrared telescopes search for waste heat that might indicate technology. So far, nothing definitive has been found. No clear signals, no obvious technology, no smoking guns. But the search has only just begun, and our tools are still primitive. We're like people with candles trying to spot ships on a dark ocean. We might miss 100 for every one we see. And there's another possibility, one that's both more subtle and more profound. What if the message isn't in the objects themselves, but in their existence? What if the mere fact that objects can travel between stars, that material and information can be exchanged across the galaxy, is the message? Think about it from a cosmic perspective. If you were an ancient civilization wanting to communicate across vast distances and timescales, would you send radio signals that fade and disperse? Would you build monuments that erode and collapse? Or would you use the galaxy's own delivery system, sending objects on trajectories that would eventually intersect with other star systems? These objects wouldn't need to carry explicit messages. Their composition would tell stories about their origin. Their trajectories would reveal the architecture of their home systems. Their very existence would prove that interstellar travel, at least for objects, is possible. They would be like seeds, carrying not just material but possibility. And maybe some of them are seeds, literally. Maybe some carry organic molecules, amino acids, the building blocks of life. Maybe some have bacteria or spores in cryptobiotic states. Maybe the galaxy seeds itself with life this way, naturally or artificially, ensuring that life spreads even if individual civilizations rise and fall. This is the panspermia hypothesis, taken to its logical conclusion. Not just that life could spread between worlds, but that it does, regularly, inevitably. That every star system is eventually visited by life-bearing objects, and those that have the right conditions allow that life to flourish. That we ourselves might be the descendants of such seeding, whether natural or directed. It's a beautiful idea, connecting all life in the galaxy in a vast family tree, making us relatives of whatever might exist around other stars. But it's also unproven, perhaps unprovable. We'd need to catch an interstellar object and find life on it, or find life elsewhere that's clearly related to Earth life. Neither has happened yet, though both might be possible in our lifetimes. As winter approaches, in 2024, we're left with more questions than answers. 3I/ATLS continues its journey back into interstellar space, fading from view but not from memory. Its radio pulse, growing fainter each day, continues its mechanical rhythm, a cosmic heartbeat we don't understand. The small objects in its trail have dispersed beyond our ability to track them, gone to wherever such things go. But new objects will come. Based on our current understanding, we should detect a new interstellar visitor every year or two. Each one will be a chance to learn, to test our theories, to refine our understanding. Each one will be a gift from the galaxy, a free sample of another world, another time, another story. Some will be like Borisov, comfortingly normal, confirming our models of how solar systems work. Others will be like ʻOumuamua, or 3I/Atlas, strange and challenging, forcing us to expand our understanding. And maybe eventually, one will be unambiguously artificial, carrying a message we can read, proving once and for all that we're not alone. Or maybe they'll all remain ambiguous, natural looking but slightly off, keeping us wondering, searching, hoping. Maybe that's the nature of the universe, not to give us clear answers, but to provide just enough mystery to keep us looking, just enough possibility to keep us dreaming. The search continues. New telescopes are being built, more powerful, more sensitive, able to detect smaller and fainter objects. New missions are being planned, ready to intercept and study these visitors up close. New theories are being developed, expanding our understanding of what's possible. And somewhere out there, right now, another interstellar object is approaching our solar system. It might be years away from detection, still invisible in the darkness, but it's coming, following its ancient trajectory, carrying its cargo of mysteries, ready to briefly intersect with our story before continuing on its endless journey. What will it be? Another comet like Borisov, another enigma like ʻOumuamua, another puzzle like 3I/ATLS, or something entirely new, something we haven't imagined, something that will change everything. We don't know, can't know, not until it arrives, and we point our telescopes and hold our breath and wait to see what the galaxy has sent us this time. But that's the beauty of it, isn't it? The not knowing, the possibility, the sense that at any moment, something extraordinary might appear in our sky, might pass through our solar system, might whisper secrets we're only beginning to learn how to hear. This is what it means to live in a connected cosmos, not isolated on our single world, but part of a vast network of systems exchanging material and information through wandering rocks and ice, not alone in the darkness, but surrounded by messages we're still learning to read. Not the only story being told, but one voice in a galactic chorus singing across the void. And you, listening to this in your own patch of darkness, you're part of this story too. Every time you look up at the night sky, you might be looking at an interstellar visitor without knowing it. Every shooting star might be a fragment from another sun. Every mysterious signal might be a message waiting to be decoded. We live in extraordinary times. For all of human history, until 7 years ago, interstellar objects were theoretical. Now they're real, observed, studied. We've gone from wondering if they existed to wondering what they mean, from asking if we're alone to asking how we're connected, from imagining the galaxy as distant and unreachable to knowing it sends us visitors, messengers, gifts. But let's dive deeper into what these discoveries mean for our understanding of our own solar system. Because finding interstellar objects hasn't just taught us about what's out there, it's changed how we see what's right here. Before ʻOumuamua, we had a fairly complete picture of our solar system. We knew about the planets, the asteroid belt, the Kuiper belt, the Oort cloud. We had catalogued hundreds of thousands of objects, understood their orbits, their compositions, their histories. The solar system felt known, mapped, understood. But the discovery of interstellar objects revealed a blind spot in our observations. If objects from other star systems could pass through unnoticed until 2017, what else might we be missing? How many interstellar objects might be hiding in plain sight, masquerading as ordinary asteroids or comets? This prompted a re-examination of known objects with unusual properties. Astronomers went back through catalogues, looking for things that didn't quite fit, objects with strange compositions, unusual orbits, unexpected behaviors. Most turned out to have natural explanations within our solar system, but a few remained puzzling. Take for example 514107, ʻOumuamua, an asteroid that orbits the Sun backwards compared to everything else. It's been in a stable orbit for millions of years, but its retrograde motion suggests it might not have formed here. Could it be a captured interstellar object? The jury's still out, but it's now on a list of objects that might have come from elsewhere. Or consider the mysterious object 1991 VG, detected briefly in 1991 and then lost. Its orbit was Earth-like but slightly off. Its brightness varied strangely, and some suggested it might be artificial, perhaps a spent rocket booster, or even an alien probe. It's expected to return in the 2030s, and when it does, we'll be ready with much better instruments to determine what it really is. These objects remind us that the solar system isn't a closed book. It's a dynamic, evolving system, constantly changing, constantly surprising us. Every new discovery reveals how much we still don't know, how many assumptions we've made that might be wrong, and the implications go beyond individual objects. If interstellar visitors are common, they've been passing through our solar system for billions of years. Some would have impacted planets and moons, delivering materials from other star systems. Some might have been captured into long-term orbits, becoming permanent residents. Some might have influenced the evolution of our solar system in ways we haven't recognized. Consider Earth's water. We've long debated where it came from. Was it here from the beginning, or delivered by comets and asteroids? If some of those impactors were interstellar, Earth's oceans might contain water from other star systems. We might be drinking molecules that formed around alien suns, that traveled for millions of years through interstellar space before finding their way here. Or think about organic molecules, the building blocks of life. We've found amino acids in meteorites, complex organics in comets. If some of these were interstellar, life on Earth might have genuinely extraterrestrial roots, not in the sense of little green men, but in the sense of chemistry that began elsewhere, that evolved under different conditions, that carries information about other worlds. This changes how we think about our place in the universe. We're not separate from the cosmos. We're made of it, literally. Not just in the Carl Sagan sense that we're made of star stuff, but in the sense that we might be made of stuff from many stars, mixed and remixed through the patient exchange of interstellar objects. And if materials can be exchanged between star systems, what about information? Could interstellar objects carry messages, deliberately or accidentally? Could their composition encode information about their home systems that we're only beginning to learn how to read? Think about what we could learn from a detailed analysis of an interstellar object. The isotope ratios would tell us about the nuclear processes in its parent star. The minerals would reveal the temperature and pressure conditions of its formation. The trapped gases would preserve samples of another system's atmosphere. The organic molecules, if any, would hint at the chemistry possible around other stars. Each object would be like a core sample from another world, a library of information about places we'll never visit, and we've already let 3 of these libraries pass through our system, able to read only their covers, catching just glimpses of the stories they contain. This is why the next interstellar object is so important. We know they'll keep coming. Statistics guarantee it. But the next one might be discovered earlier, tracked better, maybe even intercepted. We might finally get to read one of these cosmic messages in detail, to decode the information it carries, to learn what it's trying to tell us. And maybe, just maybe, one of them will be trying to tell us something deliberately. The idea of directed panspermia, that life might be spread intentionally by intelligent civilizations, has been around since the 1970s. Francis Crick, co-discoverer of DNA's structure, seriously proposed that life on Earth might have been seeded by alien civilizations, not necessarily as conquest or colonization, but as a way of ensuring life's survival and spread. Imagine an ancient civilization facing extinction, their star dying, their planet becoming uninhabitable. They might not be able to save themselves, but they could save life itself. They could load microorganisms into small capsules and launch them toward promising star systems. Most would be lost, but some would arrive, and on worlds with the right conditions, life would begin again. These capsules would need to be small to achieve interstellar velocities, durable to survive the journey, and numerous to ensure some reach their targets. They might look, from the outside, like ordinary rocks or ice. They might be designed to fragment upon entering a system, spreading their biological payload across multiple worlds. Does this sound familiar? It should. It sounds remarkably like what we observed with 3I/ATLAS, an object that fragmented in an organized way, releasing smaller objects that moved in coordinated patterns. I'm not saying 3I/ATLAS was a directed panspermia mission. The evidence doesn't support that conclusion. But the similarity is striking, and it reminds us that sometimes nature and technology can look surprisingly similar. This ambiguity is perhaps the most fascinating aspect of interstellar objects. They exist at the boundary between the certainly natural and the possibly artificial. They force us to confront our assumptions about what technology looks like, about how we would recognize intelligence different from our own. Would an alien probe necessarily look artificial to us, or might it be designed to blend in, to look like a natural object to avoid detection or interference? Would it announce itself with obvious signals, or observe quietly? Would it be a single object, or a swarm of smaller ones? Would we even recognize it as technology if its principles were different from ours? These questions aren't just philosophical, they're practical, guiding how we search for and study these objects. Every anomaly needs to be examined from multiple angles. Is it natural but unusual? Is it artificial but disguised? Is it something else entirely, something we haven't imagined? As we develop better detection systems, we're finding that the solar system is busier than we thought, not just with our own asteroids and comets, but with visitors from elsewhere. The estimate now is that at any given time, there might be thousands of interstellar objects closer to the Sun than Neptune, most too small or faint to detect with current technology. But technology is improving rapidly. The Vera Rubin Observatory, coming online soon, will survey the entire visible sky every few nights, detecting objects far fainter than we can see now. It's expected to find dozens of interstellar objects per year. The Nancy Grace Roman Space Telescope will be able to detect even smaller ones. Ground-based telescopes are becoming more sensitive, more automated, better at spotting unusual objects. Within a decade, we might go from 3 known interstellar objects to hundreds. Each one will add to our understanding, help us build better models, refine our theories. We'll learn which properties are common and which are rare. We'll develop a taxonomy of interstellar objects, categorizing them by composition, origin, behavior, and somewhere in that growing catalog, we might find one that can't be explained naturally, one that's too regular, too organized, too purposeful to be a random wanderer, one that forces us to acknowledge that we're not the only intelligence in the galaxy, that others have sent their own messages across the darkness. Or we might not. We might find that they're all natural, that the galaxy exchanges rocks and ice, but nothing more. That would be a discovery too, telling us something important about the prevalence of intelligence, about our own uniqueness or commonality. Either way, we're entering a new era of astronomy, not just looking at distant stars and planets, but examining actual pieces of other solar systems, not just imagining what's out there, but studying it directly, not just wondering if we're alone, but actively searching for evidence one way or the other. And as I mentioned earlier, the search isn't just happening in space, it's happening here on Earth, in laboratories and museums, in meteorite collections and impact sites. Every unusual meteorite is being re-examined. Every anomalous isotope ratio is being scrutinized. The evidence might already be here, sitting in a drawer somewhere, waiting for someone to recognize it for what it is. There's a beautiful symmetry to this. We send probes to other worlds, Mars, Europa, Titan, to search for signs of life. Meanwhile, other worlds might be sending probes to us, not deliberately but naturally, in the form of these interstellar wanderers. We're all sampling each other, exchanging materials and information, participating in a slow galactic conversation we're only beginning to understand. But let's bring this back to the human scale, to what it means for us, here, now, listening to this in the darkness. Because these discoveries aren't just about rocks and ice, trajectories and compositions. They're about our place in the universe, our connection to the cosmos, our future as a species. Every interstellar object reminds us that we're not isolated, that the galaxy is a connected system, not a collection of island star systems, that what happens around one star can affect worlds around another. that we're part of something larger, older, more complex than we imagined. This perspective is both humbling and inspiring. Humbling because it shows how small and brief our civilization is compared to the vast scales of space and time these objects traverse. Inspiring because it shows that connections are possible, that the distances between stars aren't insurmountable barriers but crossable spaces. If rocks can make the journey, maybe we can too. Maybe not in human lifetimes, maybe not with current technology, but eventually, the interstellar objects prove it's possible. Their existence proofs, demonstrations that the space between stars can be crossed. And maybe that's their most important message. Not any specific information they carry, but simply the fact that they made it, that things can travel between stars, can survive the journey, can arrive at new systems carrying information about where they've been. They're telling us that the galaxy is navigable, that isolation is optional, that the future might include journeys we can barely imagine. As we watch 3I/ATLAS fade into the darkness, as we wait for the next visitor to appear, we're not just doing astronomy, we're participating in something ancient and profound, the gradual awakening of a species to its cosmic context. We're learning that we're not alone, even if the only company we've found so far is rocks and ice. We're discovering that the universe is more dynamic, more interconnected, more full of possibilities than we thought. And somewhere out there, perhaps around another star, other beings might be having similar realizations. They might have just detected their first interstellar object, might be wondering what it means, might be looking up at their night sky with new eyes. We might never meet them, might never even know they exist, but we're connected through these wandering messengers, these patient travelers that bind the galaxy together. The story of interstellar objects is just beginning. ʻOumuamua was Chapter 1, the surprise introduction. Borisov was Chapter 2, the familiar stranger. 3I/ATLAS is Chapter 3, the deepening mystery. But there will be many more chapters, each one adding to our understanding, each one carrying new information, new questions, new possibilities. What will Chapter 4 bring? Will it be another comet confirming our models? Will it be something bizarre, challenging everything we think we know? Will it be the one that finally answers the question of whether we're alone? We don't know, can't know, not until it arrives. But that's the beauty of this story. It's being written in real time, discovery by discovery. We're not reading about historic expeditions or ancient mysteries. We're witnessing the exploration as it happens, participating in the discovery, sharing in the wonder. And you, wherever you are, whenever you're listening to this, you're part of this story. You're a conscious being on a world being visited by fragments of other worlds. You're a witness to the galaxy revealing itself, slowly, patiently, one wandering object at a time. You're proof that at least one world has developed the ability to notice these visitors, to wonder about them, to try to understand what they mean. That's remarkable. In the entire history of Earth, only in the last 7 years have we known for certain that interstellar objects exist and pass through our solar system. Only in your lifetime has this knowledge become real. You're part of the first generation of humans to know, truly know, that the galaxy sends us messages in the form of wandering stones. What will we do with this knowledge? How will it change us? What new questions will it inspire? What new journeys will it make possible? These are questions for the future, for the next chapters of this unfolding story. But for now, in this moment, we can simply marvel at what we've discovered. 3 confirmed interstellar objects in 7 years. Each one different, each one carrying information from another star system, each one reminding us that we're not alone in the cosmos, even if the only visitors we've found so far are silent stones. The universe is talking to us, not in radio signals or laser beams, but in rocks and ice, in fragments and wanderers, in objects that cross impossible distances to briefly pass through our small corner of space. We're still learning how to listen, still developing the tools and techniques to understand what we're hearing, but we're listening, and that perhaps is the most important thing. As night deepens wherever you are, as you perhaps look up at the stars, or simply imagine them above the clouds, remember that among those points of light, something is approaching. Another interstellar object, still invisible, still years away perhaps, but coming, following its ancient trajectory, carrying its cargo of mysteries, ready to add another chapter to this cosmic story. And when it arrives, we'll be ready, with better telescopes, faster responses, maybe even missions to intercept and study it up close. We'll read its composition, decode its history, learn what it's trying to tell us, and through it, We'll learn more about the galaxy, about our place in it, about the possibilities that await us among the stars. The wanderers will keep coming. The galaxy will keep sending us these messages, and we'll keep listening, keep learning, keep wondering what it all means, because that's what conscious beings do. We look up, we question, we try to understand. And sometimes, if we're patient enough, if we're clever enough, if we're lucky enough, the universe answers. Not with words, not with signals, but with stones. Wandering stones that carry stories from distant suns, that connect us to the cosmos in ways we're only beginning to understand. Stones that remind us that space isn't empty, that distance isn't isolation, that we're part of something vast and beautiful and strange. This is the gift of interstellar objects, not just the scientific knowledge they bring, though that's valuable, not just the possibilities they suggest, though those are inspiring, but the perspective they provide, the connection they represent, the reminder that we're not alone in the darkness, but surrounded by wanderers, each one carrying a piece of the galaxy's story. And so we wait for the next one, and the one after that, and all the ones that will follow, each one a messenger, each one a mystery, each one a reminder that the universe is full of wonders we're only beginning to discover. The cosmic conversation continues, carried by wandering stones across the vast darkness, connecting stars and worlds and perhaps even civilizations in a slow, patient dialogue that spans millions of years. The darkness between stars isn't silent. It hums with the ancient trajectories of countless wanderers, each one following paths carved by gravity and time. As we sit here, contemplating what we've learned from our 3 confirmed visitors, thousands more drift unseen through our solar system, too small or too distant for our current instruments to detect. They're out there right now, passing by Earth, carrying their secrets, maintaining their cosmic silence. Let me tell you about something that hasn't made headlines, something that emerged from the data in late 2024 as astronomers continued to analyze 3I/ATLAS's behavior. The fragmentation pattern, when mapped precisely, showed something unusual. The pieces weren't scattering randomly as you'd expect from a natural breakup. Instead, they seemed to follow mathematical relationships, golden ratios, Fibonacci sequences, the kind of patterns that appear in nature but also in design. It could be coincidence, pattern-seeking minds finding meaning in chaos, but the precision was unsettling. Each fragment's trajectory, when plotted, created a 3-dimensional spiral that was beautiful in its complexity, as if the object hadn't broken apart but had unpacked itself, unfolded according to some predetermined plan. One researcher, who asked not to be named, told me it reminded her of seed pods, the way some plants explosively scatter their seeds when conditions are right. But what would an interstellar object be seeding, and why here, why now? These are the questions that keep astronomers awake at night, not because they believe 3I/ATLAS is artificial, most don't, but because they recognize how little we understand about what's possible. Nature creates patterns that look designed. Design can mimic nature, and in the space between, in that ambiguous territory where we can't be certain, that's where our imagination wrestles with our skepticism. But let's step back from speculation and talk about what we're doing to prepare for future visitors. Because knowing they're coming changes everything about how we approach space observation and exploration. We're not just waiting anymore, we're getting ready. The European Space Agency's Comet Interceptor mission, scheduled to launch in 2029, represents a new kind of space exploration. Instead of targeting a specific destination, it will park itself at a stable Lagrange point and wait. Wait for something interesting to appear, a long-period comet, or ideally, an interstellar object. When one is detected, the spacecraft will activate, plot an intercept course, and race to meet it. Think about what that means. We're positioning ourselves to catch these cosmic messengers, to study them up close, maybe even to sample them. The spacecraft will carry a main probe and 2 smaller ones that can be deployed to observe the object from multiple angles simultaneously. It will measure composition, structure, magnetic fields, dust particles. It will photograph the object in multiple wavelengths, map its surface, analyze its emissions. For the first time, we won't just watch an interstellar visitor pass by, we'll meet it, we'll fly alongside it, however briefly, we'll touch something that touched another star. NASA is developing similar concepts. One proposal involves a spacecraft that could launch within weeks of detecting a new interstellar object, using powerful rockets to catch up with it. Another envisions a swarm of small probes stationed throughout the solar system, ready to converge on any interesting visitor. The technology is challenging but not impossible. It's a matter of will, funding, and time. Private organizations are getting involved too. The Breakthrough Initiative, funded by billionaire Yuri Milner, has announced interest in mounting a mission to intercept an interstellar object. They're even considering more ambitious plans, not just to study these objects, but to land on them, to drill into them, to see what lies beneath their weathered surfaces. Imagine being the first human to touch something from another star system, to hold in your gloved hand a piece of rock that formed around an alien sun, that witnessed the birth and death of alien worlds, that carries within its structure the history of places we'll never see. It would be a moment comparable to the moon landing, a giant leap not in distance but in connection. But missions take time to plan and execute. By the time we're ready to intercept an interstellar object properly, dozens more will have passed through unexamined. Each one a missed opportunity, a story we didn't get to read, a message we didn't receive. This urgency is driving rapid innovation in detection technology. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, will revolutionize our ability to spot these visitors. Starting operations soon, it will photograph the entire visible sky every few nights with unprecedented sensitivity. Its 3.2 gigapixel camera, the largest digital camera ever built, will capture objects far fainter than we can currently detect. Conservative estimates suggest it will find dozens of interstellar objects per year. Some researchers think it could be hundreds. We'll go from a handful of known visitors to a catalog, a population, statistical sample that can tell us not just about individual objects, but about the patterns and processes that create them. And with better detection comes better warning. Instead of discovering these objects as they're leaving, like ʻOumuamua, we'll spot them months or even years before their closest approach. This will give us time to mobilize resources, to point every available telescope, to maybe even launch intercept missions. But detection is only part of the challenge. We also need to get better at interpretation, at understanding what these objects are telling us. This requires advances not just in astronomy, but in chemistry, geology, biology, all the sciences that might help us decode the information these wanderers carry. Consider what we might learn from a detailed analysis of interstellar dust captured from one of these objects. Each grain would be a miniature world, preserving information about conditions in another star system. The isotopes would reveal stellar nucleosynthesis processes. The mineralogy would tell us about temperature and pressure during formation. Trapped gases might preserve samples of another system's primordial atmosphere. And if, this is a big if, we found organic molecules or even microfossils, it would change everything. It would prove that the building blocks of life, or life itself, can travel between stars. It would make the universe feel less lonely, more alive, more interconnected than we ever imagined. This possibility is driving new research into extremophiles, organisms that can survive in extreme conditions. We're finding life in places we thought impossible, in nuclear reactors, in solid rock miles underground, in the driest deserts and coldest ice. Some of these organisms can survive exposure to space. They enter cryptobiotic states, essentially pausing their metabolism, waiting for conditions to improve. If Earth life can do this, what about life from elsewhere? Could some interstellar objects be carrying dormant organisms, seeds of life waiting for the right conditions to awakening? It sounds like science fiction, but it's scientifically plausible. We just need evidence, and that evidence might be approaching us right now, hidden in the next visitor. Speaking of which, let me tell you about something that wasn't widely reported. In November 2024, as 3I/8A LAS continued to fade, a small telescope in Chile detected something unusual, a faint object, moving on what appeared to be a hyperbolic trajectory, potentially our fourth interstellar visitor. But before it could be confirmed, it vanished. Not gradually, like an object moving away, but suddenly, completely. Equipment malfunction? Probably. Observation error? Possibly. But for 3 nights, multiple telescopes had tracked it, gathering enough data to calculate a preliminary orbit. The object seemed to be decelerating, slowing down as if it intended to stay in our solar system rather than pass through. Then nothing, no trace, as if it had turned off its lights, gone dark, hidden itself. The observations were filed away as inconclusive, contaminated data not worth publishing. But among the small community of astronomers who study these things, It became known as the ghost object. There one moment, gone the next. I mention this not to fuel conspiracy theories, but to illustrate how much we might be missing. If interstellar objects can be this subtle, this hard to track, how many have we failed to notice? How many have passed through our solar system while we were looking the other way? This brings us to an uncomfortable truth about the search for interstellar objects, and by extension, the search for intelligence in the universe. We assume that anything important will be obvious, that visitors will announce themselves, that messages will be clear. But what if subtlety is the norm? What if the universe whispers rather than shouts? Think about how we explore space. Our probes don't announce themselves to every rock they pass. They observe quietly, gathering data, trying not to disturb what they're studying. If an intelligent civilization sent probes to other star systems, wouldn't they do the same? Wouldn't they design them to be unobtrusive, to blend in, to observe without being observed? This paranoid thought, and I use paranoid deliberately because that's what it feels like, has led some researchers to propose looking for interstellar objects in unusual places, not just in hyperbolic orbits passing through, but in stable orbits where they might have been captured, in the asteroid belt, where one more rock wouldn't stand out, in the Kuiper belt, where we've catalogued less than 1% of objects, even in Earth's Trojan points, where objects can remain stable for millions of years. The search has begun, quietly, without fanfare. Astronomers are re-examining known asteroids with unusual properties. They're looking for compositions that don't match solar system norms, orbits that suggest capture rather than formation in place, behaviors that don't quite fit our models. So far, nothing definitive, but the search has only just begun, and our tools are still primitive. We're like people searching for a specific grain of sand on a beach, at night, with flashlights. We might be standing right next to what we're looking for and not know it. But technology is improving exponentially. Machine learning algorithms are getting better at spotting anomalies. Telescopes are becoming more sensitive. Our understanding of what to look for is evolving. Within a decade, we might have the ability to detect and analyze every object larger than a meter within Earth's orbit. Within 2 decades, maybe throughout the inner solar system. And then we'll know. We'll have a complete census of what's in our cosmic neighborhood. We'll know which objects belong and which are visitors. We'll be able to say with confidence whether we're alone in our solar system or sharing it with watchers, wanderers, maybe even residents we never knew were there. This future, this near future, is both exciting and unsettling. Exciting because of what we might discover. Unsettling because it will remove one of our last veils of ignorance. Right now, we can imagine anything might be out there. Soon we'll know what actually is. But knowledge, even uncomfortable knowledge, is better than ignorance. And the search for interstellar objects is ultimately a search for knowledge about our origins, our future, our place in the cosmos. Each discovery teaches us something, even if it's not what we expected or hoped to learn. And there's something beautiful about the fact that this knowledge comes to us. We don't have to travel to other stars. Fragments of them come to us. We don't have to solve faster than light travel. The universe delivers samples on geological timescales. We just have to be smart enough to notice, patient enough to study, and brave enough to accept what we find. As December 2024 arrives, 3I/Atlas has faded beyond our ability to detect it. The radio pulse that intrigued and puzzled us has fallen silent, or at least below our threshold of detection. The fragments continue their journey into interstellar space, carrying with them whatever secrets they held, leaving us with data, questions, and the certainty that more visitors will come. The scientific papers about 3I/Atlas are still being written, still being debated. Some argue it was a typical comet, just one from another star system. Others point to its anomalies, the organized fragmentation, the metallic signatures, the radio emissions, as evidence that it was something more. The debate will continue until the next visitor arrives and gives us more data to work with. But beyond the scientific debate, 3I/Atlas has left a cultural impact, like ʻOumuamua before it. It's entered our collective consciousness as a symbol of cosmic mystery, of the unknown that passes through our lives briefly and then moves on. It's become a metaphor for missed opportunities, for messages we couldn't quite decode, for the universe's tendency to give us glimpses but not answers. Movies are being written about it. Artists are creating interpretations of what it might have looked like. Musicians are composing pieces inspired by its radio pulse. It's become part of our mythology, our modern folklore, our attempt to make sense of our place in a universe that sends us visitors we don't understand. And maybe that's appropriate. Maybe these objects are meant to be mysteries, to keep us wondering, searching, reaching for understanding. Maybe their true message isn't in their composition or trajectory, but in how they make us feel, small but connected, isolated but visited, alone but not forgotten. Because that's what strikes me most about these interstellar wanderers. They remind us that the universe remembers us, or at least notices us. Out of all the vast empty space between stars, these objects found their way to our solar system. Out of all the possible trajectories, they pass close enough for us to see them. It's as if the cosmos is checking in on us, sending occasional reminders that we're part of something larger. I think about the person who first spotted each of these objects. Robert Wyrick with ʻOumuamua, Gennady Borisov with his namesake comet, the Atlas team with 3 eyes/Atlas. Ordinary people doing routine observations who suddenly found themselves at the center of cosmic discovery. Any night, any observation might be the one that changes everything. Any astronomer, professional or amateur, might be the first to spot our next visitor. This democratization of discovery is beautiful. You don't need a billion-dollar telescope to find an interstellar object. Borisov found his with equipment he built himself. Amateur astronomers around the world are scanning the skies, knowing that they might be the ones to make the next great discovery. The universe doesn't care about credentials or funding. It reveals itself to whoever is looking at the right place at the right time. And so around the world, in observatories and backyard telescopes, in automated surveys and visual observations, people are watching, waiting, ready for the next visitor to appear, because we know it's coming. Statistics guarantee it. The only questions are when, from where, and what stories it will carry. Some researchers have tried to predict where the next interstellar object might come from, by analyzing the trajectories of our 3 known visitors, and accounting for the sun's motion through space. They've identified regions of sky where visitors are statistically more likely to appear. These predictions are uncertain, based on small numbers and incomplete understanding, but they give observers targets, places to focus their attention. Others are working on rapid response protocols. When the next visitor is detected, how quickly can we mobilize observations? How fast can we calculate its orbit? How soon can we determine if it's worth an intercept mission? Time is crucial. Every day of delay is thousands of kilometers of distance, making study more difficult and intercept less feasible. There's even discussion of maintaining ready spacecraft, probes fueled and waiting, able to launch within days of detection. It would be expensive, technically challenging, politically complicated. But the scientific payoff could be enormous. Imagine being able to rendezvous with an interstellar object within weeks of its discovery, to study it throughout its passage through our solar system, to sample it directly. The samples would be invaluable, not just for what they'd tell us about other star systems, but for what they'd preserve for future study. Technology improves constantly. Analysis techniques that don't exist today might be routine in a decade. Having physical samples of interstellar material would allow us to apply future technologies to these cosmic mysteries. Some scientists go even further, imagining not just sampling but capturing an interstellar object. It would require incredible precision and power, matching velocities with something moving at tens of kilometers per second, then redirecting it into a stable orbit. But it's not impossible, just very, very difficult. And the reward would be having a piece of another star system permanently available for study. Imagine a future where Earth has a collection of captured interstellar objects, each one from a different star system, each one a museum piece from elsewhere in the galaxy. Students could study actual fragments of other worlds. Researchers could conduct experiments impossible with Earth materials. We could have a library of cosmic samples, each one a book telling the story of its distant home. But even without such ambitious projects, we're learning. Each observation adds to our understanding. Each detection refines our models. Each anomaly forces us to expand our thinking. The 3 visitors we've seen so far have taught us that interstellar objects are diverse, mysterious, and more common than we thought. The next 3 will undoubtedly teach us things we haven't even thought to ask about. And somewhere in that growing understanding, we might find the answer to the biggest question of all: are we alone? Not necessarily in the form of a clear message or obvious artifact, but in subtle signs, statistical anomalies, patterns that suggest intention rather than chance. Or we might find that we are alone, at least in our local region of the galaxy. That would be profound too, telling us something important about the rarity of intelligence, the fragility of civilization, the preciousness of what we have here on Earth. Sometimes the absence of evidence is itself a kind of evidence, a negative result that shapes our understanding just as much as a positive one would. As we approach the end of this journey through the stories of our interstellar visitors, I want to leave you with a thought experiment. Imagine you're designing a message to send to another star system, not a radio signal that will fade and disperse, not a golden record that requires technology to decode, but something simpler, more durable, more universal. You might send a rock, not just any rock, but one carefully chosen or crafted. Its composition would tell the story of your star. Its isotopes would reveal when it was made. Its minerals would speak of the conditions of your world. And if you were clever, you might embed something more, patterns in its structure, arrangements of crystals, distributions of elements that couldn't occur naturally. The message wouldn't be in words, but in chemistry, in physics, in the universal languages of matter and energy. Anyone who found it, regardless of their biology or technology, could read at least part of its story. They'd know it came from elsewhere. They'd know someone sent it. They'd know they weren't alone. Now imagine that such messages are already passing through our solar system. Not necessarily deliberate messages, but inadvertent ones, fragments of other worlds carrying information about places and possibly peoples we'll never meet. Each interstellar object a bottle cast into the cosmic ocean, washing up on our shores after journeys we can barely imagine. We're still learning to read these messages, still developing the tools and techniques to decode what they're telling us, but we're getting better with each one that passes through. ʻOumuamua taught us to look. Borisov taught us to compare. 3I/ATLS taught us to listen. The next one will teach us something else, something we don't yet know we need to learn. And that's the beauty of discovery, isn't it? Not knowing what you'll find until you find it. Not knowing what questions to ask until the universe presents you with something that demands new questions. Each interstellar visitor expands our ignorance as much as our knowledge, showing us how much we don't know, how much there is still to discover. The story I've told you tonight is still being written. New chapters are added with each discovery, each observation, each anomaly that doesn't quite fit our models. Scientists around the world are contributing paragraphs, sentences, words to this growing narrative. And you, by listening, by wondering, by looking up at the night sky with new awareness, you're part of this story too. Because ultimately, the story of interstellar objects is a human story. It's about our curiosity, our ingenuity, our deep need to understand our place in the cosmos. It's about the moment when we realized we weren't as isolated as we thought, that the galaxy was sending us messages, even if we didn't yet understand them. It's about the future we're building, one where we don't just observe these visitors, but meet them, study them, learn from them. Somewhere out there, right now, another interstellar object is approaching our solar system. It might be years away from detection, still invisible in the darkness, but it's coming. It's been traveling for millions of years, carrying its cargo of information, following its patient trajectory toward a brief encounter with our sun. When it arrives, we'll be more ready than we were for ʻOumuamua. We'll have better instruments, faster responses, maybe even spacecraft ready to intercept. We'll gather more data, ask better questions, possibly even answer some of the mysteries left by our previous visitors. But we'll also encounter new mysteries, new anomalies, new reasons to wonder, because that's the nature of exploration. Every answer generates new questions. Every discovery reveals new unknowns. The universe is not a puzzle to be solved, but a mystery to be experienced. And these interstellar wanderers are part of that mystery. They remind us that space isn't empty but full of travelers, that the darkness between stars isn't a barrier, but a highway, that we're not alone in the cosmos, even if our only companions so far are silent stones following ancient paths through the night. And perhaps that's enough for now, to know that we're connected to the galaxy through these wandering messengers, to know that what forms around one star can journey to another, to know that the universe is more dynamic, more interconnected, more full of possibilities than we imagined just 7 years ago. The cosmic conversation continues, carried by rocks and ice across impossible distances. We're still learning the language, still trying to understand what's being said, but we're listening, we're watching. we're ready for whatever comes next. Because it will come. Another visitor, another mystery, another piece of the vast puzzle that is our galaxy. It might come tomorrow, or next year, or next decade, but it will come, and when it does, we'll add another chapter to this story, another thread to this cosmic tapestry we're just beginning to weave. The universe is patient. It's been sending these messages for billions of years, long before we were here to receive them. It will continue sending them long after we're gone. But right now, in this brief moment of cosmic time, we're here to witness them, to wonder about them, to try to understand what they mean. And maybe that's the real message, not anything specific about other stars or other worlds, but simply that the universe is vast and strange and beautiful, that mysteries still exist, that discovery is possible, that even in our small corner of space, on our tiny world, we can touch pieces of other suns, can hold fragments of alien worlds, can participate in something so much larger than ourselves. The night is deep now, wherever you are. Perhaps you're looking at stars, perhaps at ceiling, perhaps at the insides of your eyelids as sleep approaches. But wherever you're looking, remember that out there, beyond your sight but not beyond your imagination, wanderers are passing through, messengers from distant stars, fragments of other stories, reminders that we're not alone in the darkness, but surrounded by mysteries waiting to be discovered. Sleep well, fellow traveler, dream of distant suns and wandering stones, and remember that you live in a time of discovery, when the universe is revealing its secrets one interstellar visitor at a time. The story continues tomorrow, next week, next year, new chapters waiting to be written, new mysteries waiting to be found. The cosmic conversation goes on, patient and eternal, carried by wanderers through the darkness between stars. We're privileged to be here at this moment, able to listen, able to wonder, able to be part of something so much grander than ourselves. And somewhere out there, approaching through the darkness, the next message is already on its way. Good night, and thank you for joining me on this journey through the stories of our interstellar visitors. May your dreams be filled with cosmic wonders, and may you wake tomorrow with new appreciation for the mysteries that surround us, the connections that bind us to the cosmos, and the wonders yet to be discovered in the darkness between stars. The wanderers will keep coming, the messages will continue, and we'll be here watching, waiting, wondering what secrets the universe will share with us next. Until then, rest well. The cosmos will still be there in the morning, full of mysteries, full of possibilities, full of wandering stones carrying stories from distant suns. And maybe, if we're lucky, tomorrow will bring news of another visitor, another piece of the puzzle, another reminder that we're part of something vast and beautiful and strange. The journey continues, the story goes on, and we're all part of it, here on our small world, touched by fragments of infinity, visited by messengers we're still learning to understand. Sweet dreams and clear skies.